Hello and greetings, everyone. My name is John Morrow. I am a professor of materials science and engineering at Penn State University and author of the textbook Materials Kinetics, Transport, and Rate Phenomena. In this series of videos, I would like to go through each of the chapters of the book and give you a lecture on each of those topics. Feel free to ask me any questions in the comments below. And yeah, there's a lot more depth in the book, so please read the chapters in the book too as you go along. So let me share my screen and we will get started with lecture one, which is on thermodynamics versus kinetics. So I'm going into this lecture with some assumption that you already have some background in basic thermodynamics. And as this introductory lecture to this course on kinetics, I'm going to compare kind of the domain of thermodynamics versus that of kinetics. So the field of classical thermodynamics is largely concerned with equilibrium. What is the nature of equilibrium? Which states are more stable than other states? And there are various definitions of equilibrium, and it depends on the constraints that are imposed on the system. But one of my favorite definitions of equilibrium comes from the great late Professor Richard Feynman, who said in his book on statistical mechanics that equilibrium is, quote, when all the fast things have happened, but the slow things have not. Now, I know what you're thinking. Surely you're joking, Mr. Feynman. How can this be the definition of equilibrium? It does beg the question, what is fast and what is slow? These are relative terms, fast compared to what, slow compared to what, and it really depends on your perspective as an observer or as somebody who is conducting the experiment. So this definition of fast and slow depends on your perspective as an observer, and it's really up to you to pick the relevant timescale for the experiment that you are conducting. So let's make an example here of coffee and cream in a cup in a room. So at the beginning of the morning here, let's suppose that you have brewed a cup of coffee and pour a little bit of cream into that coffee. On the time scale of a few seconds, that coffee and the cream reach a chemical equilibrium with each other. At that point, you can either take a sip of the coffee cream mixture, or if you wait on a time scale of, say, an hour or so, the coffee cream mixture will reach a temperature equilibrium with its surroundings. So this is a thermal equilibrium that occurs on an intermediate time scale. If you wait even longer, say on the order of a few days, the coffee cream mixture will reach a vapor equilibrium with the atmosphere, and all that would be left was this residue of what used to be coffee in the bottom of the cup. So I ask you, which one of these is the true equilibrium? The coffee cream mixture, the thermal equilibrium, or the vapor equilibrium? The answer is any one of these can be the true equilibrium depending upon what it is that you want to study. If you are interested in studying the mixing of the coffee and cream, then the relevant equilibrium that you study would be on the shorter time scale. If you are studying, say, Fourier's law and are studying the transfer of heat, then the relevant equilibrium for your study would be this temperature equilibrium on the intermediate time scale. If you are studying vapor equilibrium, then the relevant time scale is in fact the one that occurs on this longest time scale, vapor equilibrium. So even though Feynman's definition of equilibrium seems a little bit flippant at first, it actually has a lot of insights pointing to the importance of choosing the appropriate time scale for your experiment. So when we compare thermodynamics versus kinetics, a really helpful diagram is this two-state system shown here, where this shows the Gibbs free energy of various states of the system on the y-axis versus some sort of reaction coordinate or position coordinate here on the x-axis. There are two minima in this Gibbs free energy diagram that corresponds to this double well potential. The first minimum here shown in blue is the higher of the two minima. This is a metastable state. It is a locally stable state, but it is not the global minimum in free energy. And then this second minimum here on the right that corresponds to the purple circle is the lower Gibbs free energy, in this case, the global minimum in the free energy. So let's suppose that we start off in this state, this blue state on the left-hand side. If this were a chemical reaction, these would be the reactants going then to the products on the right-hand side. Or maybe this is just some particular structure or configuration of your material system under study. In either case, there are two relevant quantities here in this two-body diagram. The first is this difference between the free energy of the initial state versus the free energy of the final state. And this difference here is denoted as delta G. This is the free energy of reaction. It's just the difference in free energy between the two states. And this is a thermodynamic quantity, a purely thermodynamic quantity that tells you the relative stability of these two states. So whichever one has the lower Gibbs free energy is the more thermodynamically stable state. So this thermodynamic quantity tells you whether the reaction is feasible and which product is in the more stable equilibrium. It's basically giving you a relative stability of states where a lower Gibbs free energy indicates a greater stability of that state. The other relevant quantity on this two-body diagram is the difference between your initial state here and then this transition state, which represents the activation barrier that has to be overcome in order to make the transition. And this is labeled here as G star, or the free energy of activation, also known as the activation free energy. And this is a kinetic quantity because this is telling you how large of a barrier the system has to overcome in order to make the transition between the initial and the final states. So this G star is a kinetic quantity, and the kinetics are telling you how fast is the reaction and what are the intermediate states that the system visits on its path from this initial state to this final state. So even on this simple two-state system, we've got two of the most important quantities for thermodynamics and kinetics. The delta G, this free energy of reactions, a thermodynamic quantity, and G star, the free energy of activation, which is a kinetic quantity. So thermodynamics is largely concerned with determining the relative stability of different states under a given set of conditions for materials processes. So if you were at, say, a particular temperature, a particular pressure, you've got a particular chemistry under study, thermodynamics is going to tell you which phases are more stable than others. Kinetics, the word kinetics here comes from the ancient Greek kinesis, which means movement or motion. And kinetics is largely concerned with determining the rates of materials processes and the evolution of systems under some set of conditions. And kinetic processes depend on both the thermodynamic driving force for that process to occur, as well as the kinetic rate parameters. One of the general themes of this course is that any process really has two most important underlying factors. First, what is the thermodynamic driving force for that process to occur? And second, what are the relevant kinetic rate parameters that tell you how fast that process occurs? Now, one of the classifications of materials processes is whether or not it is spontaneous. A spontaneous process is defined as a process that takes the system to a more thermodynamically stable state. So if we are under normal conditions for material scientists, meaning a constant pressure or isobaric system and a constant temperature or isothermal system, then the relevant quantity here to determine the stability of states is the Gibbs free energy. If it were constant volume instead of constant pressure, then we would be dealing with the Helmholtz free energy. But staying in this domain here of Gibbs free energy, the lower that we go in Gibbs free energy, the more thermodynamically stable the state is. So in this case, going from this left-hand state here in blue overcoming this barrier and ending up in this purple state on the right. This has a lower Gibbs free energy compared to the initial state, and moving to a lower Gibbs free energy means that the final state is more thermodynamically stable. This, therefore, is a spontaneous process defined by the delta G, this free energy of reaction, being negative, being less than zero. This spontaneous process, though, just because a process is spontaneous, that doesn't tell you anything about the barrier. It doesn't tell you anything about the pathway for how to get from the initial state to the final state. And therefore, just because a process is spontaneous, that doesn't tell you anything about the kinetics of that process. What are some examples of spontaneous process in everyday lives here? Ice melts at room temperature. This is because at room temperature, of course, the entropy of liquid water is more dominant over the enthalpy of the crystalline ice, and therefore the minimum in Gibbs free energy for water at room temperature is in its liquid state. Therefore, ice melting at room temperature is a spontaneous process. Other examples include water flowing downhill, sugar dissolves in water, heat flows from a hotter object to a colder object, a gas expands to fill an empty vessel, and iron exposed to oxygen and water forms rust. All of these are spontaneous processes. They will happen on their own without any work being done on the system, and they happen on their own because they lead to a lower Gibbs free energy. How about another example of a spontaneous process? Another one of these is the conversion of diamond to graphite under ambient pressure and room temperature conditions. So diamond, here this shows the Gibbs free energy diagram of diamond versus graphite. Diamond actually has a higher Gibbs free energy compared to graphite at room temperature and ambient pressure. This means that the conversion of diamond to graphite is a spontaneous process, one that will happen on its own. But I ask you, how many of you who have, say, diamond jewelry or a Vickers diamond indenter in the lab, have you ever seen diamond spontaneously convert to graphite? And I'm assuming the answer is no. And this goes back to the point that just because a process is spontaneous doesn't mean that you will actually observe it, because this doesn't tell you anything about the time scale over which this process occurs. So spontaneous transformation of diamond to graphite generally does not occur at room temperature and atmospheric pressure because the kinetics are too slow for us to observe this process. Although graphite is more thermodynamically stable, the barrier that has to be overcome is simply too high to be able to observe this on our human timescale under our normal conditions. Now, the opposite of a spontaneous process is, of course, a non-spontaneous process. With a non-spontaneous process, we are moving from a state that has a lower free energy to a state that has a higher free energy. In other words, the delta G, the Gibbs free energy of reaction here, is positive. So during a non-spontaneous process, the system moves to a less thermodynamically stable state. In other words, it has a higher free energy. This requires some external source of energy to drive this process, because this is not something that would occur on its own. In our everyday lives, there are many examples of these. So filling a tire with air is an example of that. You know, at equilibrium, this would drive the pressure within the tire to be the same as the atmospheric pressure. In order to make the pressure within the tire significantly higher, we need to perform work on it. So this is an example of a very useful non-spontaneous process. Photosynthesis is a non-spontaneous process that plants perform to convert solar energy into chemical energy. Refrigeration is another very common example of a non-spontaneous process that requires work in order to maintain a temperature difference between the colder environment within the refrigerator and the warmer environment outside. Skiing uphill. water purification. Taking a kinetics exam is another example of a non-spontaneous process. If I put the exam on your desk and you just sit and stare at it, it does not complete itself. It requires work to do so. So what do all of these non-spontaneous processes have in common? They all require work. Now let's review some fundamental thermodynamic quantities that we will be making use of throughout this course. The way that I remember these is in this kind of 2x2 matrix here, this mnemonic shown here, where we start up here in the upper left quadrant with the internal energy. The internal energy of the system represents all of the energy of the interactions between electrons with each other, electrons and nuclei, atoms as a whole interacting with other atoms, and all of this is determined by all of those forces that lead to repulsion or attraction. And if you add up all of those, like if you take the book, for example, there's atoms that bond together all of the pages here, and all of those energies put together, if you sum it up, that gives you the total internal energy of the system or of this particular object. And that is often denoted as U. Sometimes you will see internal energy denoted as E, but this is where we start. Now, if we move from the left-hand column to the right-hand column, this involves adding PV, or in other words, adding the pressure times the volume, the pressure of the surroundings times the volume of the system. And if we do that, if we add PV to our internal energy, the quantity that we get is the enthalpy, which is typically denoted as H. And the way to think of this is if I were to sort of magic this book into existence here, not only do I have to account for all of the internal energy here, U, but also the fact that I am displacing part of the atmosphere in order to make room for the volume of this book. So the pressure of the surroundings, the pressure of this atmosphere that I'm displacing, times the volume of the amount of displaced atmosphere, when that contribution is added to the internal energy, that gives you the enthalpy. So this is the relevant quantity whenever we are at some isobaric, if we have an isobaric condition where the pressure is non-zero. If I were to sort of magic this into existence in outer space where the pressure is zero, in that case, this PV term would be zero, and the enthalpy of the book would be exactly equal to the internal energy of the book. So in other words, whenever we are at isobaric conditions where we've got some pressure of the surroundings, the relevant side here is this right-hand side. Now, in going from the upper row to the lower row, what we are doing is moving to a free energy. And the way we get a free energy is by incorporating the entropic contribution to those energies as well. And that involves subtracting Ts. In other words, subtracting the absolute temperature, T, times the entropy of the system, S. Absolute temperature is represented in units of Kelvin. So this is always a positive quantity, and entropy is also always greater than or equal to zero. So this is a positive quantity times a positive quantity with a minus sign in front. So this is always going to lead to a lowering of the free energy of the system. Now, if we take the internal energy here, U, and subtract T times S, what we get is the Helmholtz free energy. The Helmholtz free energy is the relevant free energy if we have constant volume conditions instead of constant pressure conditions. Sometimes we work with Helmholtz free energy because either the conditions are appropriate for that or it's more convenient to work with Helmholtz free energy. But most of the time, in a practical sense, most of our experiments that are done as material scientists are done under constant pressure conditions. rather than constant volume conditions. And therefore, the quantity that is most relevant for us is usually the Gibbs free energy. Likewise, going from the upper row here that has the enthalpy and then subtracting Ts, this gives us the Gibbs free energy of the system. The way that you can remember this is goldfish are hell without tartar sauce. G equals H minus Ts. That's the easy way to remember this equation for Gibbs free energy. Now, let's manipulate this a little bit. If we've got our Gibbs free energy, G equals H minus Ts, goldfish are hell without tartar sauce. G here is the Gibbs free energy. H is the enthalpy. T is the absolute temperature in units of Kelvin. Never, ever, when you're doing thermodynamics or kinetics, never use Celsius and never use Fahrenheit. Always use Kelvin. And then the S here represents the entropy of the system, which we'll cover in a little bit. Now, when we are dealing with whether a process is spontaneous or non-spontaneous, the relevant quantity is not the Gibbs free energy in an absolute sense, but rather the change of Gibbs free energy between two different states. So if we look at the change of Gibbs free energy, we've got the delta operator here, delta meaning change. So the change of the Gibbs free energy, we put change on the left-hand side and change on the right-hand side. So delta G equals delta H, the change of enthalpy, minus here the change of the product of the temperature and the entropy of the system. Now, this delta works exactly the same way as a differential operator. So when you apply this to the product of T times S, we need to use the product rule in order to distribute that out. So that means that we apply the delta here to the S multiplied by the first term. That is this first term here. So it's minus T delta S, and then minus, then do the opposite. So the second term here, S times delta T. Now, most of the time, we are operating under constant temperature conditions. That means that most of the time, this delta T is considered to be 0. And if that is considered to be 0 for isothermal conditions, then that term goes away. And what we are left with is the much more familiar way of writing the change of Gibbs free energy, which is delta G equals delta H minus T times delta S. So this is telling you that although the relative stability of different states is governed by delta G, there are really two contributions to that delta G. There's the delta H contribution and the minus T delta S contribution. And so much of thermodynamics is concerned with this kind of epic battle, if you will, between the change of enthalpy versus the change of entropy, where, for a given process, enthalpy may push the system towards one direction, but entropy may push it in another direction. And what is it that governs whether the process is spontaneous or not? That depends on which one wins between enthalpy and entropy. And the key parameter that determines that is the temperature of the system, T. Because if this temperature of the system is 0, if we were at absolute 0 temperature, then this entropy term completely goes away. And the Gibbs free energy is entirely determined by the enthalpy of the system here, delta H. Likewise, if we are at an extremely high temperature, say the limit of infinite temperature, then this entropic term here completely overwhelms the enthalpic term. So at extremely high temperatures, the state is completely governed by the entropy term, and the enthalpy term doesn't matter. Now, most of the time, we're not at absolute 0 and we're not at infinite temperature, but we're somewhere in between. And therefore, there is this balance between the enthalpy contribution and the entropy contribution that tilts towards enthalpy at lower temperatures and tilts towards entropy at higher temperatures. So the way that we can visualize this is in this 2x2 matrix here, where if we consider, what makes the process spontaneous versus non-spontaneous under these different conditions. So if we've got delta G equals delta H minus T delta S, there are, two possibilities for each of the delta H or the delta S. We could go to a lower enthalpy. Delta H is less than 0. This is enthalpically favored. That is this first column here. Or we could go to a higher enthalpy, which is not favorable because a higher enthalpy means a higher Gibbs free energy. So this would be enthalpically unfavorable here in the right-hand column. Likewise, the delta S can be either positive or negative. If the entropy goes up, that is thermodynamically favored, because if this delta S term goes up, then the Gibbs free energy goes down. So increasing entropy is favorable. Delta S greater than 0 is favorable here in the first row. On the other hand, decreasing the entropy of the system, delta S less than 0, is unfavorable. And that is what's listed in the lower row shown here. Now, sometimes you'll have a process where the enthalpy goes down and the entropy goes up. That is a process that is spontaneous at all temperatures, because the enthalpy contribution is driving the free energy downward. The entropy contribution is also driving the free energy downward. So there's no competition here between enthalpy and entropy in this upper left quadrant. They both want the same thing, and this process is spontaneous regardless of the temperature. Likewise, if we go to the lower right quadrant here, where the enthalpy increases and the entropy decreases, this is enthalpically unfavorable and entropically unfavorable. So this is a process that really does not want to occur at any temperature. This is a non-spontaneous process at all temperatures, because regardless of the temperature, this process would cause an increase of the Gibbs free energy of the system. Now, the more interesting cases are shown here with the yellow backgrounds. This is where we've got some competition between enthalpy and entropy. So enthalpy wants one thing and entropy wants something else. So if we start here in the upper right quadrant, this is a process where the enthalpy increases. The delta H is greater than 0, and the entropy also increases. The delta S is greater than 0. So here, entropically, this process is favored. The entropy goes up. So from a purely entropy point of view, this process wants to occur. However, the enthalpy also goes up, so this is enthalpically unfavored. The change of enthalpy is driving the Gibbs free energy up. The change of entropy is driving the Gibbs free energy down. So there's a competition here. And which one wins between enthalpy and entropy depends on the temperature of the system. Entropy always wins at higher temperatures, because this temperature here is what is weighting the entropy term. If the temperature is low, the entropy term matters less compared to the enthalpy term. If the temperature is high, then this entire term outweighs the enthalpy term. So here, this process is spontaneous at high temperatures, because high temperatures is where entropy wins, and entropy wants this process to occur because the delta S goes up. So this upper right quadrant, this is spontaneous at high temperatures where entropy wins, and non-spontaneous at low temperatures where the enthalpy wins. If we flip that around here in the lower left quadrant, this is a process that is enthalpically favored because the delta H is less than 0, but entropically unfavorable because the entropy goes down. So enthalpy wants the process to occur. Entropy does not want it to occur. Again, entropy always wins at high temperatures. So at high temperatures, this process is non-spontaneous. The enthalpy always wins at low temperatures. And so that means that the process is spontaneous at low temperatures. So anytime that we're given a process, it is helpful to think about that process, not just in terms of thermodynamic driving force versus the kinetic rate of the process, but also, digging deeper into that thermodynamic driving force. What does enthalpy want to do versus what does entropy want to do? And like where's the crossover temperature where one part becomes dominant over the other? So in this next part of the lecture, I would just like to briefly review the three laws of thermodynamics. The first law of thermodynamics is the most straightforward. Of course, we all know that the first law states that energy is conserved. This is something that goes back to Newton's days. It has been known for a very long time, the conservation of energy. In other words, energy is neither created nor destroyed. It is merely converted among different types of energy. And one of the fundamental equations here for thermodynamics is dealing with this conservation of energy and accounting for the transformation among various types of energies, whether it's heat, work, chemical energy, many different types of work here, including mechanical work via compression or expansion, electrical work, the creation of interfacial energy by the creation of interfaces, magnetic energy, polarization energy, deviatoric strain energy. These are all different types of energies, different forms of energies that can be converted amongst each other. They all have the same units of joules. And so much of engineering is about how to convert among different types of energies. So, for example, the solar cell is concerned with converting radiation energy, photons from the sun, into electrical energy. So there's really no confusion about the first law of thermodynamics. The second law of thermodynamics is a bit more complicated to understand. And you can see here three kind of common statements of the second law of thermodynamics. This first one here, due to Clausius, states heat can never pass from a colder to a warmer body without some other change connected therewith occurring at the same time. So this is kind of, it's really more of a consequence of the second law of thermodynamics rather than an intrinsic statement of the second law. You note here that Clausius never mentions the word entropy, which is really, the basis of the second law. Planck gets much more to the point here in his statement. Planck says, every process occurring in nature proceeds in the sense in which the sum of the entropies of all bodies taking part in the process is increased. So, any thermodynamic process has the system that we study, as well as the surroundings around it. And if you take the system plus the surroundings, that is the entire universe. And so summing up the entropies of the system, the entropy of the surroundings, the entropy of the universe here is going to increase. Clausius comes back with another statement of the second law, a slightly different statement, that says the same thing as Planck, but in a more succinct fashion. Clausius says the entropy of the universe tends to a maximum. So what exactly does this mean? This cartoon from the New Yorker shows a mother coming in and upset with her little son here. He's supposed to clean his room, but it is in a very disorderly state, and he's blaming entropy here. This is a statement of the second law that things that are low entropy tend toward things that are high entropy. This cartoon reflects a common misunderstanding of entropy as well, that many people consider entropy to be a measure of disorder. In other words, there's only a few number of ways that the room can be ordered, and many, many ways that the room can be disordered. And that has led people to believe that this higher entropy state is a reflection of the disorder, and that is not necessarily true. It is often true for equilibrium phases that higher entropy phases do tend toward more disorder. So for example, if you've got a crystal at low temperature, crystal is well ordered and low entropy. And if that melts at a higher temperature, the liquid state tends to be more disordered compared to the crystalline state and also higher entropy. And if you go past the boiling point to the gaseous state, the gas has a higher entropy as well as a higher degree of disorder compared to either the liquid or the crystal. And so there does, in that sense, tend to be a correlation between high entropy and high disorder. But that doesn't necessarily mean to be the case, especially when we deal with non-equilibrium systems. And also some equilibrium systems exhibit behavior like inverse melting, for example. Some systems actually, if you have a solid, a crystal, and you cool it, there can be melting upon cooling instead upon heating. And that's where this relationship between entropy and disorder actually gets reversed, where in that case, the crystal is the state that has the higher entropy compared to the liquid, although the liquid has a higher degree of disorder. So we need to let go of this notion that entropy is a measure of disorder, because it is not, although they are often related to each other. What entropy is a measure of how many different ways the system can produce a particular macrostate, or in other words, how many different microstates, how many different atomic structures or configurations are available to that system to produce a particular macrostate. So an example of that would be an egg. You know, how many different ways can this egg be intact? And there's a very few number of ways that the atoms in the egg can be positioned in such a way to have this intact egg. And so this is a lower entropy state. On the right-hand side, there are very many ways to break an egg, an exponentially large number of ways to break the egg. So the number of broken egg states greatly exceeds the number of intact egg states, and therefore the entropy of the system on the right here, the broken egg state, is greater than that of the entropy of the intact egg state on the left. Now, one of the interesting consequences of the second law of thermodynamics is the arrow of time, also known as Boltzmann's arrow of time. Entropy is the only physical quantity that requires a particular direction of time, the so-called arrow of time. This is in contrast to, say, Newtonian mechanics, where if you take Newton's laws of motion, you can do a time reversal and send everything back to where it was previously in time, whether it's billiard balls on a pool table. If you just reverse the directions of all of the forces, you could recover the initial state of the balls on the pool table. In a similar sense, if you just follow Newtonian mechanics, let's suppose that you have an ice cube in a glass of water that's above the freezing point of water. And what we observe is that the more ordered configuration of the ice, this lower entropy configuration of the ice, will melt, increasing the entropy of the system over time. Now, according to Newtonian mechanics, if you take all of those water molecules after the ice cube has melted and just reverse the direction of motion for all of them, that you could recover the ice cube. In other words, the ice cube could reform in that glass of water at room temperature or at some temperature above the melting point. There's nothing in Newtonian mechanics that prohibits that. In fact, that is the natural result of making all the times go to minus times, reverting the times. Why do we never see that? Why have we never seen that happen? That is because the number of ways that the atoms could kind of coordinate their motion to spontaneously produce an ice cube at room temperature in liquid water, the number of ways to do that is overwhelmingly small compared to the number of ways of not making the ice cube. So in other words, considering the randomization of all the velocities of the water molecules, it is overwhelmingly probable that that the water will stay in the liquid state rather than just making an ice cube at room temperature. And this gets back to entropy. This means like the number of different ways that something can happen is going to be more entropically favored. Now, getting back to this direction of time, as one goes forward in time, the second law of thermodynamics states that the entropy of an isolated system can increase, but not decrease. In other words, moving forward in time moves the universe from a state of lower entropy to a state of higher entropy, and not the other way around. And the reason for that is that it's overwhelmingly probable to do so, because it's overwhelmingly probable to move from a macrostate that has a very few number of possibilities, a very few number of microstates, towards a macrostate that has a much greater number of possibilities. And this is why the second law of thermodynamics is valid. It's valid from a purely probability argument, that it's just much more overwhelmingly probable for a system or for the universe to sample the states that have a greater number of possible microstates. So this entropy in the kitchen here is an example of time's arrow. The broken egg state exists in time after the intact egg state, never the other way around. This is also called the Humpty Dumpty rule. All the king's horsemen and all the king's men could not put Humpty Dumpty together again. This intact egg state exists before the broken egg state and never the other way around. And that is because of the second law of thermodynamics. There is a great video here from Brian Greene. I'd encourage you to watch that. It's a BBC video where he gets into some of the inherent physical meaning of entropy, which is a good complement to this particular lecture. Now let's consider this thought experiment, this Gedanken experiment that was proposed by Maxwell regarding the concept of entropy. Maxwell proposed, what if we have a system here that is composed of two subsystems here with a wall in between these two subsystems? So you've got the left subsystem here and the right subsystem here. And in this system, there is a mixture of two different gases. One of them is the red gas here, shown by the red atoms, and the other one is the blue gas, shown by the blue atoms. And they start in an initially mixed state. Now, what Maxwell does is he proposes, what if there were some little demon here that is sitting at this wall between the two subsystems, and the demon can open and close or close the wall depending upon whether it's a blue atom or a red atom that is traveling from the left to the right or the right to the left. And the demon chooses to either open or close the wall to let all of the red gas atoms travel to the right, but never to the left, and all the blue gas atoms to travel to the left and never to the right. And over time, based on this selective opening and closing of the wall by Maxwell's demon, the system that is initially mixed, that initially has a good mixture between the red and blue gas atoms, ends up being unmixed at the end, where all of the blue gas is on the left, all of the red gas is on the right. This is a lower entropy system compared to what we started with. So we went from a higher entropy state to a lower entropy state, which at its surface, the reason that Maxwell proposed this is that this could be a violation of the second law. So let me ask you, does this violate the second law of thermodynamics? And the answer is no, it doesn't violate the second law of thermodynamics, because this demon is performing work on the system. This demon is using the information about the identities of the particles here to open and close the door. all of this takes work. And although the entropy of this particular system is going down, because of all the work performed by the daemon, the entropy of the surroundings outside of the system is increasing by at least as much as the entropy of the system is lowered. So overall, the entropy of the universe is still increasing. So this does not violate the second law of thermodynamics. Now, the third and final law of thermodynamics is the statement about absolute zero temperature and the entropy at absolute zero. Like the second law, there have been many different statements of the third law of thermodynamics. This first one is due to Nernst, and Nernst said at absolute zero, meaning at absolute zero temperature, the entropy change in chemical reactions is zero. Now, Planck has a slightly different statement of the third law. He says at absolute zero, the entropy of a substance is zero. Note the difference here. Nernst says at absolute zero temperature, the entropy change is zero. So the delta S is zero. Planck is actually making a stronger statement here. He's saying that the S equals zero. The entropy is zero. So S equals zero versus delta S equals zero. Another statement here is due to Lewis. Lewis has a more restrictive statement compared to Planck. Planck is stating at absolute zero, the entropy of a substance is zero. He doesn't say anything about what the substance is. Lewis says at absolute zero, the entropy of a perfect crystalline solid is zero. So Lewis is saying this only applies for perfect crystalline solids. And this is actually a reflection of the misunderstanding that we discussed earlier, that the misunderstanding here is that entropy is a measure of disorder, and therefore only a perfectly ordered system, or in other words, a perfect crystal, would have zero entropy. And this is a misunderstanding that still survives today among some folks. Planck's statement is actually the better statement of the third law of thermodynamics, because how do we get zero entropy? We get zero entropy if the macrostate of the system is determined by one and only one configuration. That doesn't say anything about whether that configuration is ordered or disordered. That only means that the system's trapped in one and only one configuration. And if you take the logarithm of that to get the entropy would be zero. So at absolute zero temperature, transitions between microstates are not possible, and therefore the macrostate of the system is entirely determined by one and only one microstate. So Planck's statement here is really the best, most general statement of the third law, because regardless of what the system is, at absolute zero temperature, transitions between microstates are not possible. And so the entropy of any system is zero at absolute zero, regardless of the level of order or disorder in that system. Another statement of the third law, which is really a corollary of the third law, is due to Nernst, and that is the absolute zero of temperature can never be reached because, in principle, you'd have to have it in a system in contact with another system with negative temperature to extract everything out, and that is unobtainable. But the most fundamental statement of the third law, the one that I hope you will all remember, is the statement due to Planck: at absolute zero, the entropy of a substance is zero. Now, this gets us back, these discussions of the second and third laws of thermodynamics get us back to the microscopic basis of entropy, which is due to Ludwig Boltzmann, one of my favorite scientists. This is his tombstone, which is in Vienna, Austria. One of my former students was actually kind enough to take a copy of the textbook and bring it here to Boltzmann's grave in tribute to Boltzmann, and sent me this photo. So shout out to Jonathan for doing that. Thank you so much. He knows, what great affinity that I have for Boltzmann. Boltzmann was a wonderful teacher. He's somebody who cared a lot for his students. He didn't care about kind of the high society and all formalities and so on. He just loved science, and he loved students, and he loved learning, and he loved teaching. Now, Boltzmann is known as the father of statistical mechanics. Statistical mechanics is the field that connects thermodynamic quantities to the underlying atomic structures of materials. So Boltzmann is the one who proposed this notion um, that the thermodynamic quantities of a material, really any of the properties of the material, are determined by what are the different atomic configurations that that material can have, and what are the probabilities that those atomic arrangements will occur. Now, this, at the time, in the late 19th century, this was a highly controversial topic for a couple of reasons. First, it was not widely accepted that materials were made of atoms. Um, Even though the concept of atoms goes back to BC times, to ancient Greece with Democritus, who was the first person to propose the existence of atoms. In the 19th century, most of the prominent scientists did not believe that atoms existed. And in fact, when Boltzmann gave his lecture on proposing statistical mechanics in Vienna to this physics society there, another scientist, esteemed scientist at the time, Ernst Mach, the speed of sound guy, was in the audience. And at the end of Boltzmann's lecture, Mach stood up and said, "Herr Boltzmann, I do not believe that atoms exist," and sat down, just being completely dismissive of Boltzmann's entire body of work. Now, another problem for Boltzmann was not just um, his embrace of the concept of atoms, but also he was using a branch of mathematics that was considered to be immoral. He was using probability and statistics and treating it as an intrinsic part of the description of physics of materials. In other words, different atomic configurations have certain probabilities of occurring, and if we do a suitable weighted average over those different configurations according to their probabilities and the properties associated with those probabilities, that gives us the overall expected behavior, or the average behavior and properties of the system. Now, back in the 19th century, proper mathematicians were not studying probability and statistics because it was deemed that the only thing that it was useful for was for gambling, so for an immoral act. And therefore, anyone who studied probability and statistics was viewed negatively. And Boltzmann went even further, not just using it, but building it in as a fundamental part of his description of physics. So he was, taking two controversial topics, putting them together, and building this new field of study based on that. And his theories were widely rejected and ridiculed. He was bullied terribly by other people. And unfortunately, this did not end well for him. He didn't deal very well with this bullying. And when he and his family were on vacation in Trieste in northern Italy, and his family was out at the beach, he actually hanged himself. Um, he ended his own life. He just couldn't take it anymore, and he was buried in an unmarked area. And his work was largely forgotten for about 20 years. It was actually Max Planck who kind of rediscovered Boltzmann's work. And it was Planck who was the first person to actually get the value for Boltzmann's constant. It never occurred to Boltzmann to actually figure out what that value was. So it was actually Planck who figured out the value of Boltzmann's constant, and Planck already had his own constant h, so this is appropriately named as Boltzmann's constant. At that time, Einstein had done some of his uh, pioneering work proving the existence of atoms, and so atomic theory was getting more widespread acceptance, at least among some of the younger scientists at the time. And unfortunately, Boltzmann did not live to see this. So, about 20 or so years after Boltzmann's death, his work was gaining new respect. And the good people of Vienna actually dug him up and buried him again, giving him this proper tombstone shown here. And he's buried among some of his musical heroes, like Mozart, I believe, is also there. And at the top of his tombstone, you'll see the engraving of Boltzmann's equation for entropy, which is, one of the most important equations in statistical mechanics and thermodynamics. Is Boltzmann's equation for entropy, where he stated that the entropy of the system here, S, this is not delta S, this is S, the absolute entropy of the system is equal to some constant, Boltzmann's constant K, times the logarithm of the number of microstates that yield a particular macrostate. Okay, and Boltzmann's constant here, K, as determined by Planck, is just the gas constant divided by Avogadro's number. In other words, it's the measure of kind of the energy capacity on a molar basis, but divided by Avogadro's number gets it to you on this atomic basis. It's 1.38 times 10 to the minus 23 joules per Kelvin, Boltzmann's constant. So that gets multiplied by the logarithm of the number of microstates that yield a particular macrostate. So if you have only one configuration of atoms that is possible, so one configuration of atoms that determines the entire macrostate of the system, you put a 1 in here, the logarithm of 1 is 0, and the entropy is 0. So why is Planck's statement of the third law valid? Because if you have a number of microstates equal to 1, which you necessarily do at absolute zero temperature, at absolute zero, this omega always equals 1. Taking the logarithm of that gives you 0, which means that the entropy of the system is 0 in the limit of absolute zero temperature. If you've got a system that has a large number of microstates, in other words, the system is visiting many different atomic configurations, each one of those atomic configurations that is visited contributes to the overall macrostate of the system. And then you've got the logarithm of some larger number here, which gives you a positive entropy. The second law of thermodynamics is valid because the universe is tending towards macrostates that have a greater number of possible microstates. And why is that? It's simply because it's overwhelmingly probable to do so, based on the randomization of atomic velocities and the directions that things are moving. It's overwhelmingly probable that the universe is tending towards a system with higher entropy because the number of possible microstates that are visited is increasing. So Boltzmann's equation here is critical for understanding the fundamental basis for both the second law of thermodynamics and the third law of thermodynamics. Now, why is there a logarithm? Why does Boltzmann's equation for entropy have this logarithm here? Why is it not just, say, K times omega? And this is because of the very special properties of the logarithm function in mathematics. And we can understand this by considering a system that is a composite of two subsystems. So if we've got an overall system here that is divided into two subsystems, 1 and 2, the volume of subsystem 1 is V1, the volume of subsystem 2 is V2. What's the total volume of the system? That's obvious, right? Volume is an extensive property. That means that we add up the volumes of the subsystem to get the total volume of the system. So V is equal to V1 plus V2. That is because of the extensive nature of volume. Likewise, what's the enthalpy of the composite system? The enthalpy of the composite system is simply the enthalpy of subsystem 1, H1, plus the enthalpy of subsystem 2, H2, because enthalpy is an extensive property. Entropy is also an extensive property, so it must also satisfy this same rule. The entropy of the composite system is the entropy of subsystem 1, S1, plus the entropy of subsystem 2, S2. So S equals S1 plus S2. Why is there a logarithm? If we go back to the microscopic basis of entropy, the entropy of subsystem 1, S1, is equal to Boltzmann's constant times the natural log of the number of microstates in subsystem 1, omega 1. So S1 equals K log omega 1. Likewise, for subsystem 2, the entropy of subsystem 2, S2, equals Boltzmann's constant times the logarithm of omega 2. the number of microstates in subsystem 2. Now we know, given that entropy is an extensive quantity, that the entropy of the total composite system is equal to S1, the entropy of subsystem 1, plus S2, the entropy of subsystem 2. Now, how do we make that work from a mathematical point of view? Since the number of possible microstates of the composite system is the product of that of the subsystems, the logarithm is required to make those entropies additive. In other words, if there are omega-1 number of possible microstates on the left, omega-2 number of possible microstates on the right, the total number of possible microstates of the composite system is not the sum of the two, it's the product of the two. You could be in the first microstate here on the left and then have any number of the microstates on the right. Or you could be in the second microstate here on the left and then any number of microstates on the right, and so on. So the total number of microstates that are possible for the composite system is omega-1 times omega-2. So the entropy of the composite system, S, is equal to Boltzmann's constant times the logarithm of the product of omega-1 and omega-2. And the logarithm is here because the logarithm of the product is the sum of the logarithms of those individual factors here. So this is equal to Boltzmann's constant times the log of omega-1 plus Boltzmann's constant times the log of omega-2. This first term here is S1. The second term here is S2. So the logarithm is there because of the extensive nature of the property of entropy and the fact that when you combine two different subsystems, the number of possible microstates is the product of the microstates of the subsystems, not the summation. So that is why the logarithm is there in Boltzmann's formula. So what you need to do is know your laws of thermodynamics, all three of them. The first law, energy is conserved. The second law, the entropy of an isolated system, in other words, the entropy of the universe, increases with time. And the third law, at absolute zero, the entropy of a substance is zero. The third law is valid according to Boltzmann's equation because the number of possible microstates, the number of microstates that lead to a particular macrostate at absolute zero is always 1, and the logarithm of 1 is 0. So the entropy of a substance is 0 at absolute zero temperature. The second law is valid because it is overwhelmingly probable to be valid. It's overwhelmingly probable to visit macrostates that have a greater number of possibilities compared to a fewer number of possibilities. Now, why are we doing all of this? If you're working as an industrial scientist and you're developing some new material, the customer will never come to you and tell you, I need a material that has an enthalpy of this or an entropy of this. No, we're studying this because all of these fundamental quantities, the entropy, the enthalpy, the free energy, they all tell us what the thermodynamic properties are, the physical properties that people care about for a practical use of the product, whether it is a thermal expansion coefficient, which gets back to how the volume is changing with temperature at constant pressure, the isothermal compressibility, the heat capacity under constant volume or pressure conditions. All of the properties of a material are governed by these underlying thermodynamic parameters of entropy and enthalpy, and all of them in turn are governed by the underlying atomic structures of the materials. How many different configurations are available? What are the properties associating with those configurations? And what are the probabilities that they will occur? So that's kind of the rationale for why thermodynamics is so important and why statistical mechanics is so important, because that is what is governing these properties that we care about from a more practical point of view. So again, I hope you enjoyed this lecture and got something from it. If you have any questions, feel free to reach out and let me know. Lecture number 2 will be on irreversible thermodynamics. This is the subfield of thermodynamics that specifically deals with non-equilibrium systems. And we're going to study this next because this is what gives the thermodynamic driving force for kinetic processes to occur. Thank you so much, and I will see you next time.